Number 61, solve for x. Log base 4 of x plus 2 minus log base 4 of x minus 3 equals log base 4 of 6. All right, this one, you just have to make sure that you realize that you've got to combine these two logs. You can't just undo separate logs when they're added or subtracted. You have to combine it into a single log using that property of logs that says if you have a difference of two logs, that's the same thing as a single log of the quotient. So this is equal to log base 4 of x plus 2 over x minus 3. So that's crucial that you first do that. Then that's equal to log base 4 of 6. And now it's really nice because there's a log on both sides. They're both base 4, and you can exponentiate both sides, base 4, and essentially cancel those out and get that the fraction x plus 2 over x minus 3 equals 6. But you can see how important it is to remember that a difference of two logs has to be combined into this quotient, because that's very different and very important. All right, then to solve this equation, you can multiply both sides by x minus 3 to clear that denominator. And x plus 2 is equal to 6x minus 18, right? Because that's over 1, so that cancels. And here you distribute. So then you can get all your x's on one side, subtract x. Over here you get 5x. Add 18 over here, you get 20. 5x equals 20, so x is 4. And then remember, you just have to check to make sure that you're not going to be taking log of a negative number if you plug your solution into the original equation, and we're good with x equals 4. So that's the answer. Number 62 and 63 are using the pH formula. Negative log of the hydronium ion concentration is how pH is defined. So this first one says determine the pH that has hydronium ion concentration of 6.28 times 10 to the negative 7th. So for that one, you just plug that number into the formula here. So you're going to be taking negative log of 6.28, negative log of 6.28 times 10 to the negative 7th power. And that you can just type into your calculator. Negative log of 6.28 times 10 to the negative 7. .2, usually they just round it to one decimal place. So 6.2 is the pH of that particular substance. Going backwards, number 63, if you are given the pH is 3.4, then you set that equal to the negative log of the hydronium ion concentration. So 3.4 equals negative log of, let's just call it x. So to solve for x, you need to first multiply both sides by -1 or divide both sides by -1, same thing, to make that a positive log. Isolate that logarithm. And then that's base 10. So remember, to undo base 10, you want to exponentiate base 10. Or just use the definition, right? If log base 10 of x equals negative 3.4, that means that 10, the base, to the power, negative 3.4, is equal to x. And then they just want you to type this into your calculator to get that in proper scientific notation. Here, let me use this calculator. It doesn't glare as much. So 10 to the negative pH is basically how you figure out the hydronium ion concentration. So that's 3.98 times 10 to the negative fourth. All right, so remember that you've got this decimal, and then this E is for exponential or scientific notation, and that gives you the power of 10. So it's 3.98 times 10 to the negative fourth is the proper scientific notation for that hydronium ion concentration. All right, number 64. A sample of 778 grams of a radioactive substance decays according to the formula A of T equals 778 e to the negative 0.038 T. All right, so the coefficient there, that 778, is always the initial amount, because if you plugged in 0 for T, then you would get e to the 0, which is 1. So at time 0, you have an initial amount equal to 778. So they kind of told you that twice. All right, I'm writing down this function. So we have this amount at time t is equal to this number, which is the initial amount, times this exponential decay situation. When the power is negative, it's always decay. And that's what a radioactive substance does. T is time in years. It says determine how much of the substance will remain after 10 years. How much of the substance will remain after 10 years is just what's A of 10. Plug in time equal to 10. So that's just a calculator problem. 778 e to the second ln is your e to the negative 0.038 times 10. We'll calculate that power. So that's 532 approximately. 532 grams. And then it says determine what the half-life of the substance is. So half-life, by definition, half-life is the amount of time it takes to decay to half of what it initially was. So in this case, half of the initial amount is half of the 778. But what we can do is just write on this side that A of T is half of 778. And we want to set that equal to this function and solve for T to get the time that it takes until the future amount is half of what it was initially. So first thing you want to do here to solve for T is to divide both sides by 778, because you want to get that exponential by itself before you can get the variable that you're trying to solve for out of the exponent. So you divide both sides by 778, and you just end up with that 1/2 equals the exponential. And then to get T out of the exponent, you need to take ln of both sides. Ln of e to the is a inverse situation, kind of like square root squared. So you just end up with the power, negative 0.038 t equals ln of 1/2, which is just a number. And so dividing both sides by negative 0.038, the coefficient of t, will give you your answer. So that time is equal to, and when I calculate that, ln of 1/2 divided by that coefficient, negative 0.038. It turns out that's always true, that the half-life is ln of 1/2 divided by that coefficient, that rate of decay. In this case, 18.24 years is the approximate half-life of this substance.